Okay, I think I was just finishing saying something about this. Yeah.
Yeah. So, yeah. Okay.
Okay, sorry for this interruption. I think I was just reminding before moving away from the Fourier transforms properties that if you see a feature in one domain of certain width, it is not that it is a result of a specific contribution at the corresponding Fourier feature at 1 upon delta x. Every point in one domain is contributed by all the points in the other domain. And as I said, if you see a peak or discrete feature in one domain, it of course does mean while all the spectral contributions are contributing or together, they are cohering to produce that feature. That much can be said. Okay, and all right, let's move on to coherence. I briefly brought this up in the way of introducing it right in the beginning of this talk, and we're going to look at each one of them separately. There is a distinction to be made between internal coherence versus mutual coherence, and so you can immediately see if one thing has internal coherence. For example, a simple sinusoid has a high degree of internal coherence. That means that it's predictable over a certain scale. And in the case of a sinusoid, in fact, it's predictable everywhere. Once you know its phase and amplitude, there is no further information to it that you require. There is no randomness in any part of the behaviors once you are given this initial information. Similarly, a point source in the sky, a compact source in the sky is something that has high degree of internal coherence. Mutual coherence necessarily requires two things that we are comparing with, and we are seeing whether they have something in common, right? And in doing that, all the care has to be taken, as I illustrated initially, that we need to take into account variety of things that might appear to be different. And for anybody doing a blind comparison, we should ask them to guard against minor differences in the presentation of the entities and look at essentially the details, how well the details match. Okay. Now, I think I last time probably said this, or if I have not said this, there are famous Fourier pairs tied up by uncertainty principle, and you will find that they have, of course, the natural inverse dependence on the resolution widths with each other, which is governed by the uncertainty principle. You know we already looked at examples of angular response or diffraction pattern, how that is related to the aperture distribution. The one very important pair which people have exploited very profitably and has given us a rich tool is the one relating the brightness distribution in the sky or any distribution and its Fourier transform, which is a spatial coherence function. That means measurements of level of similarity that you have between the fields received at two locations in space, how similar they are, and that measure taken for all possible locations or separations and the orientations of the of the vector joining the two locations, when put together, gives you a way of obtaining the brightness distribution, even if you do not have means of measuring the brightness distribution with the desired resolution that you want. Sometimes it might require, in the context of astronomy, you might require a huge telescope, which you cannot build. But then you can appeal to this other domain. So this is one very good example of when you cannot make measurements in one of the domains, you can ask if it is possible or easier to do measurements in the other domain, which is Fourier related, and exploit that. We have already seen the temporal coherence function and spectrum, which is a common thing that we have. We have seen how the spectral response or the resolution in one of the domains will depend on the width of the time window, and it's simply related to if the time window is a rectangular one. It will have its Fourier transform, which is the sinc function, which convolves the spectrum, and that the true spectrum, and we stop seeing details finer than that response function. Okay. Now, how do we understand the internal coherence? And I think Rad gave a very, very compact description of it, which is compactness in phase space. You can ask how compact it is in the phase space. And here, phase space we're talking about, which is the common phase space that you people understand from your physics background. And it's simply the momentum space, position in momentum space. And so it has got, each one of them has got 3 dimensions. And it's a 6-dimensional system in which you ask, is what I'm looking at, if it's described in this, is it compact? Now, you can see that in the context of Fourier descriptions, you can consider the starting domain and its Fourier domain combined together, defining this phase space. And we will see exactly what corresponds to what in the subsequent discussion. So, of course, what it means is if it's compact in one domain, it is, as we have seen, the conjugate relationship between widths. If it has narrow width in one domain, it is broader width in the other domain, and so on and so forth. But in such a way that if it's one of the most compact descriptions in phase space, you will find the, much like in the position momentum space, you know that the uncertainty principle tells you that the volume cannot be narrower or smaller than h cubed. And this is taking 3 dimensions, right? Position dimensions and 3 momenta associated with those corresponding position coordinates. And you can show that basically applying the uncertainty principle in each one of the pairs of position and momentum, you can convince yourself that the volume cannot be squeezed more than h cubed. Same thing holds good. Here we have, already talking of frequencies, so the h goes away, and essentially you'll find that the volume of combined across these whatever coordinate system or whatever description you have in one domain and its counterpart, it will not exceed, cannot be smaller than unity, which is essentially saying delta t, delta nu is always equal to or greater than unity. And the same thing can be, you can have for any number of such pairs, and can in principle should be extendable to any dimension. So, but more practical things are relating to three-dimensional positions and three momenta. Okay. Whereas, as I said, mutual coherence is retained under all kinds of scalings and translation. And the examples that we showed was the two apples, which is basically, I just took a zoomed down version of the bigger apple and placed it. If I placed it somewhere else, the apple is not going to look any different to us because our brain is allowing for all the scalings and translations and even rotations. For example, even if I tilted this one of the apples, you wouldn't call it a different apple. You would look at the patterns, you would look at the shape, you would look at the other properties which are scale and translation independent, and then make the comparison. And this is exactly the care one needs to take while assessing mutual coherence. So while correlation is a tool to assess coherence and similarity, blind use of correlation will lead you to trouble, as you can see. If I were to just take two images in which the apple looks smaller or bigger, and I compute cross correlation coefficient much the way that I described, you will find correlation is not very high. But does that mean incoherence? No. So incoherence, of course, will lead to lack of correlation. That is guaranteed. There is no guarantee for the converse, which is lack of correlation need not always imply lack of coherence. One can say, sort of to be correct, lack of correlation might imply lack of or apparent lack of coherence. But then when we are trying to look for something and it's difficult to find anyway because of other reasons, including presence of noise and so on, we don't want to be tricked by trivial things that our brain is so used to take care of. And when we want machines to do it for us, we should teach the machines how to do it. Okay. So it's a compactness in phase space that implies or indicates the level of internal coherence. As I said, a point source or unresolved source in the sky would be a good example of internal coherence, which of course implies that the spatial coherence is the broadest. That means any two people observing this point source in space will see a very similar signal received from the source when the distribution is limited to a point source. And so it will show that there is high degree of spatial coherence on large scales when there is compactness in angle. So what is that compactness? That is the compactness in momentum space, right? The direction is well defined. And so that will lead to positional coherence. Similarly, an unresolved spectral line feature, a very narrow spectral line feature, will give rise to a broad temporal coherence, which you can see, and I just talked of unresolved spectral line already when I mentioned the sinusoidal wave, right? It has a very narrow feature in the spectrum, a delta function practically. And you will find that it has coherence across the entire span in time. Similarly, an unresolved temporal feature, a very narrow pulse, would have a high degree of coherence across its Fourier domain, which is the spectrum, and you will find that there is a certain phase relationship and amplitude relationship across the entire spectrum. Similarly, for people who are familiar with imaging, when you have when you have spatial coherence only at zero spacing, that means only when you stand at the same location, you see similar signals. If you move away, you will not see similar signals. If that is the case, then you are implying coherence across the angular domain. And a very beautiful example of that is the cosmic microwave background. You will find that the cosmic microwave background will give you uniform brightness practically for the entire range of angles that you can see. But it will also be something where the spatial coherence between signals received by two observers will not exist anywhere else unless the two observers happen to locate themselves at the same location. So this we already see that the widest coherence will be obtained in such cases in the other domain, of course within the constraints of the uncertainty principle. Okay, I already mentioned this, but let me elaborate on it. We have two angles, the two direction parameters, and they define basically the transverse components of the momentum vector, right? Other than the vertical one, right? Any deviation from the vertical can be taken as that defining the direction of the source in the sky, and they will have corresponding projected components of the momentum in the whatever plane you want to look at it. So the XY components of the momentum they can also be, you can characterize them in whichever way. People often use direction cosines to label them in that way. And then you will find in the XY plane, in the position domain, you will measure the spatial frequencies, the separations between two observers. And so this is the pair that in momentum space and in the corresponding position description that you will relate to. The other one is tied up with the frequency nu or f and its counterpart as a delay, which can also be thought of as a time difference or part difference, or in certain case widths. So these are the 6 parameters in phase space that we will be dealing with when we have dealing with astronomy context. You can of course identify similar ones in any other situation that you are thinking about. So as you will see, the relative locations are not important. Sorry, the relative locations are the ones that are important, not the absolute locations. Is the difference between these locations. And this is also consistent with the fact that, remember, positional translations, rigid translations of things don't change the coherence. So, okay. Now, while we, often invoke waves and so on, these are unavoidable constraints, even in the case of single photon. I will not elaborate on this, but you can get and derive your diffraction formula, which involves a lot of integration and this time, all the other mathematical details. You can arrive that by simple considerations of uncertainty principle, by considering the x component of the momentum of a photon coming at some angle, and derive the constraint on the angle of arrival, which will turn out to be lambda by d, after applying the right pair of position and momentum uncertainty and using the uncertainty principle. Okay, we are I will skip over this. I will leave that material for people to read if they want to have a look at it. But the constraints that come from uncertainty principle become relevant in containing our grid while building an instrument or using an instrument or having a measurement setup. So while astronomers' agenda is essentially to measure intensity as a function of the two sky coordinates and frequency, time, and polarization state, if you're lucky or have the resources. So you will find that the spans and resolutions in these basically decide the complexity of the instrument or the process that you're using. While we would like to be greedy and have fineness, the best fineness in each one of these and largest spans in each one of these, much like the considerations you have while you buy your, while you choose the mobile phone with the camera specs defined. You want wide angle camera with very high number of pixels and so on. But we can't do that beyond a certain point inherently because of the uncertainty constraints. And so we cannot define all of them to be to our desire mutually independently. So for example, you will find the span and resolution in intensity, which is called the dynamic range, depends on the aperture size and the spectral width and the observing time. The sky coverage and angular resolution, they for a given single instrument depends on the collecting area or the aperture area and the frequency. The frequency resolution is limited by the time over which we make the observation. That also decides the level of sensitivity. The details in time that we can see depend on how much more bandwidth you use, and so on and so forth. So I will not go into this. We already have looked at the phase space, and you will find the information is there, not just in terms of temporal frequencies. The rate of information is not just governed by the temporal frequencies. So there is also another bandwidth associated with the spatial frequencies, which are just the relative position difference that we use information over or sample the information over, where in the way of, one has seen in terms of the spatial coherence function measurement. Okay. So aperture synthesis, which is a famous technique, depends on this principle. And this uses the coherence to the highest level. We will see essentially what one is trying to do is build a big telescope, a single aperture effect. That is not possible. But if one were to build such an instrument and imagine that such imaginary instrument or aperture were available, you can ask what you will see at the focus of such an instrument. And that total electric field that you will receive will be sum of the field received by each small pieces of this aperture. Our interest is in finding the intensity. And so if you go to intensity, you will find its modulus square of this E total, which will result in, you can immediately see with your maths eye that it will be sum of lots of cross terms, and each one of the cross terms will look like Ei, Ej star, because we have taken E total and multiplied it by E total conjugate. So you will find that because the quantity of interest is intensity, which is square of the entity that we actually measure or receive, you will find all these measurements of E total modulus square will amount to summation of pairs of products, or summation of product of these pairs of electric fields. And so this is what a two-element interferometer would actually measure when we compare electric field pattern received by one observer and compare that with what the other observer received. And so in principle, all these measurements can be done with just one pair of elements. And if you have enough patience and time, you can go around measuring each one of these pairs for all possible locational separation and orientation of this separating vector, and put them together and then use the Fourier domain description to sort of take the inverse Fourier transform to get your brightness distribution. Of course, if somebody takes pity on you, gives you n antennas or n such observers, you can conduct n into n minus 1 by 2 and C2 pairs can be realized, and so many measurements can be made simultaneously. You can appeal to Earth rotation and have for example, if you have two observers sitting along east-west direction and looking at a source while it's rising, the rising source will see both these observers very, very, very much together, or sometimes at the same location in projection. Whereas the source will see them separate and standing at two different locations separated by their physical distance only when it goes overhead at the meridian. And so you will find with the same pair, if you wait for 6 hours or 12 hours, you will find the source sees you measuring different components of the of its spatial coherence function. And so by using n antennas and using Earth rotation, you can make large number of measurements, and those measurements will give you the you can go to even synthesize equivalent of Earth size aperture. People have done that. But in doing all this, the inherent feature or inherent assumption is that you are wanting to measure the mutual coherence. So I will skip over this. So what you can also see what you're actually measuring when you use this measurements is taking the sky, multiplying it by a sinusoid, okay, imaginary sinusoid, and taking the sum of this product across the entire sky, and that is the level of coherence that you will see from the sky. Now, in assessing this, you're making lots of assumptions that both the observers are seeing the same things, and they're seeing the same part of the sky. The signals received by each one of them are modified only by effects which are relating to their separation, and which you can account for. And so one can ask what those effects are. So it's not only that they're looking at different parts of the sky with different delays in arrival of the signals from that area, but they also might be moving differently with respect to the different parts of the sky. So I will not go into details of this. This is essentially the situation where a wavefront arriving from a particular source in certain direction will arrive at two different times at these locations. So this is like the translation in time. This is like equivalent of my having moved the apple from one location to the other. Now, we don't want to misled by that translation in assessing the similarity between the apples. We will allow for the shift to be a parameter. Either we decide or and correct for it through the geometrical picture that we understand or even search for it in case of any uncertainty on top of what our physical picture suggests. And which is what is done while computing the correlations. Simple physical translations are taken care of in the domain in which you're comparing. But there could be similar translations also in its corresponding Fourier domain. For example, in this particular domain, you are seeing the time of arrival, which you are correcting for without arguing about it. But if there is a translation, a similar translation in the Fourier domain of it, which is the frequency, if the frequency shifted somewhat for one observer with respect to the other observer, which can easily happen due to the Doppler, differential Doppler that might exist because of our location on the Earth being different, and our tangential velocity not being the same, being on different parts of the Earth. And so it's like a moving observer watching the same source. You will see different Doppler shifts, and you need to correct for them. But these are not apparent as time delays. They are not apparent as the shift in the domain in which you are viewing this. So you need to also check if there are translations in the other domain as well. So this is what I've said. The mutual coherence, we can ask what is different at the two locations in addition to the arrival time. So the wavefront, the Doppler shifts due to observation could be different. And so even for a coherent source in the sky, do we let these shifts destroy the mutual coherence? We know that it doesn't happen even in our thinking, nor in practice. People do recognize this and correct for this, and this is all that is related to doing the interferometry correctly. All the complications in the techniques and so on result from wanting to do this and doing it correctly. So, so my definition of it is not limited to this translations and rotations or scalings in each one of the dimensions, be it the original domain or its Fourier domain. I would like to sort of view this as any reversible transformation you do to a given entity retains its coherence with the original. So as long as you not mix the information, that it can be brought back to the same level in principle by doing appropriate operations, you have not destroyed mutual coherence. So any two things are mutually coherent to me if one can be transformed to the other through reversible transformations. You can think about it. You will be encountering situations like this in several aspects. Certainly, people doing pattern recognition and so on, even when they want to formally do this, not just by machine learning aspects, you will find that these aspects become extremely relevant. So certainly what is clear from all this is a blind correlation may reduce significantly, and it's not to be relied on. We of course want to use this as a tool, and as we do the compensation for all these possibilities, which are, remember in all this, these are linear transformations, okay? Any nonlinear transformation appears could be irreversible because of mixing of information. Any nonlinearity will reproduce in the counterparts, the Fourier description harmonics. And once they get mixed, there is no way to reassociate them unless you have kept record of what has happened, in which case you have collected more information. And have retained some level of reversibility. So essential point in all this interferometry, where the coherence, intrinsic coherence might exist and might appear to be getting destroyed by some of these things, where our main aim is to catch the same wavefront. So whatever needs to be done to catch the same wavefront coming at successive rates that are expected given the rate of change of information we expect. If all that is matched, then we are comparing apples with apples and oranges with oranges. Okay. These are just some examples of how you can get the measurements from single pair of antennas, which will give you sampling along an ellipse in general. And many such measurements from many pairs will allow you to fill the plane in which you want to gather information. This is just showing you the sampling, the visited regions of it. And then you can measure this level of similarity, which might appear like that, and in one particular case. And then you can put that together and to get an image. So what, of course, you can immediately see is, although there was a simple small source here, you got all this muck or spurious stuff around. And that is simply related to you not having sampled this entire region and not sampled it uniformly. Which means now you need to, what you've done is you have convolved a function which is 1 at locations where you see black dot and 0 elsewhere. Such a function has multiplied the true sampling that you would have had to have, or true distribution of visibilities or spatial coherence function. Having done that, you can easily see using your Fourier hat that it has convolved the true brightness distribution by the Fourier transform of this mask function, okay, which is 1 and 0 in the way I described it. And that is what has resulted in this mark here. This is like the pattern of the stars that we showed in one of the examples, where the instrumental response function has convolved, is convolved with the true distribution of stars in that part of the sky. And so you got replicas of those patterns, which you need to remove if you were to wanting to get the, so it's called dirty beam. You can call it anything else. It's also called point spread function. So to be able to do all this, you need to appeal to actual calculation of Fourier transform. So far, we've been looking at pictures and formulae which are essentially integrals and so on and so forth. So you need to be able to do these things in practice. You need to appeal to discrete versions of Fourier transforms, where it's exact set of calculations can be performed by hand or computers. And this is the discrete version of the Fourier transforms, which you must be familiar with. In using this, of course, you need to make sure that, so this will now get us to, wanting to remove all the effects that have occurred due to convolutions that happen necessarily, or some additions that happen on the way. And so this brings us to the issue of calibration, where we are trying to translate what we observe back to the information that we are after, which is the origin. So this will involve essentially undoing what has happened on the way, be it in the during the propagation of these signals in the medium, or in the way we measured it, or the limitations in our measurements. So this will involve measurements of your instrument itself, very well. The instrumental properties and any effects that are relevant to the way your information, measured information, is modified from what the original information was, is essential. So these are just some examples. I'm not going to go into any great detail of it, except to say that one will have to get to the ideal case within the uncertainties that are inherent with the process of such measurements, in addition to the uncertainty principle-based constraints. So you can improve things from the way they appear to have been measured largely, and that's been the success story in most fields, in ability to trace back the original, and that depends on how well you calibrate your system. That means how well you know your system. And this, trivially stated, is essentially an operation of divide and or subtract for things that were multiplied and or added, right? So it's a very simple statement. So when somebody asked me what do I do, my simple answer was I only divide and subtract. I don't make any positive contribution. So and that is related to the calibration aspect. If you so I will skip over these details, except to say that even in discretizing the information that we have, in fact, we have information only in discrete form, and even while obtaining that, we need to make sure that we do not suffer from something called aliasing. We don't mix information either in the time or frequency domain, and that requires looking at whatever phenomena you want to sample and record, that it is recorded at intervals or often enough that there is no mixing of information in any one of the domains. And that brings in what is called the famous Nyquist Criterion. So, which states that if you have a certain process which has got some bandwidth or rate of information, which is B, you should look at the information at intervals of twice that rate, a rate which is 1/2b. And this will ensure that you get all the information that you require. And so these are some examples you can look at leisurely. There are a variety of examples either available on the web or otherwise. You can also do oversampling. You will certainly not lose anything, but how much more you gain is dependent on the exact nature of the spread of information in the spectral domain. And we do use, wherever possible, Hermitian symmetry. So while even calibrating, you can use all that information. So this is again going back to the rate of information and how Nyquist criteria should be honored while even making these measurements. For example, even when you make measurements with this pair of observers, how close they should be standing at least certain times is decided by the Nyquist criterion. And if you don't want to mix information from one part of the sky with another part of the sky, it turns out that if you take measurements all the way down to even half a wavelength separation, then you are guaranteed not to mix information from one part of the sky with the other. Okay, I will skip over this. There are several examples of discrete Fourier transforms and the pitfalls in that process and some of the artifacts that might come, and how not to get worried about them in case your Fourier transform doesn't appear exactly the way you expect. There could be some artifacts. So how you can do interpolations if you are worried about this apparent artifacts and so on, and in general also if you want to sample your, or at least you won't get extra information, but if for presentation purposes, if it becomes important that you know the in-between values of any function that is already discretized, how to do that. So I think I don't know why that part is repeating. Okay, so these are just the pairs. You can also use these things to measure surfaces of your apertures and accuracies. You can make the measurement on a point source and measure the far field pattern, which is also important for as a part of calibration. You need to know with what function each one of the star location response has been modified. You need to know this pattern. So this is the pattern of the surface smoothness. And, after subtracting the parabolic shape and the things associated with that, you can actually go and measure micron level ups and downs or deviations from the surface. All these become important because when these will decide how your point spread function looks like. And if tomorrow you want to claim a small feature in the image that saying, oh, I see something new here, you need to ensure that it is not due to some funny response of your point spread function. So all these things become integral part of the calibration procedures. Whether you just divide or subtract depends on the simplicity of the operation that has happened. Remember that convolutions, which result in multiplication of the Fourier domain descriptions, there you can, that's where the division becomes important, or simple scale factors or gains. But if they become a function of frequency, we call them transfer functions or spectral response. So you need to divide by them. In any division, you need to ensure that you don't divide by zeros. So in places where the convolution had amounted to multiplying by a pattern which had zeros in it, the information is lost completely. You cannot recover that entirely. But there are ways to recover those. There are some deconvolution algorithms. One of them is famously known by the name clean. People can also do certain calibrations by using certain constraints. And so there are, if you have a priori some information about certain source, then you can apply those constraints and improve your calibration. And what is calibration essentially? There are a large number of unknowns that have played a role in modifying the original information. Original information itself is an unknown to you, right? There are additional unknowns that have crept in the way things got processed, and you got the final answer. Now you're trying to basically solve for, n simultaneous equations with m unknowns. If m is larger than n, you are in trouble, and so you try to get as many pieces of information as possible independently, or by other combinations of considerations of it, and try to solve for all of them. Of course, in doing all this, noise is something which is going to stop you from trying to be being able to decide everything with high degree of accuracy. There's no other way of getting over it than to just appreciate the effect it has and admit it while you quote any inferences from these measurements and the calibration. So I will skip over this. This is tied up with the just the Fourier transforms and so on, in case you people want to go through it. I encourage all of you to write at least your own Fourier transform code at least once in life and get a feel for it and make your own original, creative mistakes, and the amount that you will learn from it will be enormous. Then, of course, you can use the best available Fourier transformer routine available in the world and use that for routine use. So thanks. If you want to play with any data and understand many of these things that I've talked about, there is a piece of data on the Vela pulsar that you're most welcome to use, links to which are given to, I think, Priya and Najam. And if you need that from me, I can always pass it on to you. So thanks a lot.
Thanks, Desh. So, yeah, I think I have that Vela pulsar data. I'll put it up on the website. I'll share it. Yeah, I have it.
So if there are any questions, of course, I'm happy to answer. Although I just
Please,
realized by clicking something I stopped sharing, but I can always go back.
Yeah, so whoever wants to ask, you can unmute or you can use the chat window, whatever you prefer. Okay. I think people are just waiting to celebrate Holi. We don't even have a holiday for Holi tomorrow. That's so sad.
And a lot of care has to be taken while celebrating Holi, right? I think that's...
we are not given a holiday. We are supposed to go to work. So what are we going to do? We got to take regular class and do the usual stuff.
Start with a slide of Holi.